Good day. I'm Marc Tabadero, and I'm here to present the concept of Shannon limits on information capacity. So there are two parts that I will discuss here in this video presentation, particularly on these main topics. The first one is the discussion on the Shannon's limit of information capacity, and number two, some of the problem-solving examples. So let's go to the first part, which is the main discussion to this presentation. So, what is information capacity? It states here that it is the capacity of the system in the presence of noise that measures how much information can be propagated through a communication system. It is also known as the function of bandwidth and transmission time that displays the number of independent symbols that can be carried throughout a system in a given unit of time, wherein this information capacity is usually expressed as bit rate, or better known as bit rate per second. So we have two ways in defining information capacity. The first one is the information capacity based on Hartley's law, and the second one is the information capacity based on Shannon's limit. So Hartley's law on information capacity states that it is directly proportional to the bandwidth and transmission time of the system, where it can be expressed into this equation: I is equal to KBT, where I is equal to the information capacity, K is a constant, B is the bandwidth, and T is the transmission time. On the other hand, Shannon's limit states that it is a function of the bandwidth and signal-to-noise ratios to the system. Based on these two, Hartley's law focuses more on bandwidth and transmission time, while Shannon's limit focuses more on bandwidth and signal-to-noise ratio. So I will discuss later on what is this equation all about. But if we look on those two definitions, the use of Hartley's law is usually mentioned and aforementioned in our communications 1, wherein it states that it is equation directly proportional to the bandwidth and transmission time. However, since we are now in communications 2, this information capacity has been extended, wherein there is a limit on it that is developed by Claude Shannon, which he created the Shannon's limit of information capacity. So in the next slide, this is the equation on the Shannon's limit of information capacity. So it is expressed as I is equal to B logarithm base 2 of 1 plus S over N, where I is the information capacity in bit per second or bit rate, B is the bandwidth in hertz, and S over N is the signal to noise ratio, which is usually expressed in unitless value or no unit value. So this equation will be used some of the problems that I will present later. Okay, so I'll give the first example. So the question is, what bandwidth is needed to support a capacity of 128 kbps when the signal power to noise power ratio in dB or in decibel is 100? So if we look into this solution, we have the given signal to noise power, which is expressed in decibel, which is 100 decibel, and the information capacity is 128 kbps. We all know that this is the equation, particularly it is the Shannon's limit on information capacity. However, since the signal to noise ratio is expressed in decibel, then we need to convert into a unitless value. So it can be expressed as 10 raised to S over N in dB over 10. Now we can substitute and we get this equation. Then we substitute the given value, so we get 128 kbps over logarithm base 2 of 1 plus 10 raised to 100 over 10, where we get 3853.1839 Hz, or better known as 3.8532 kilohertz. So the second example, a radio channel has a bandwidth of 10 kHz and a signal to noise ratio of 15 decibel. What is the maximum data rate that can be transmitted using any system? So we have the given bandwidth and the signal to noise ratio respectively. So we need to find the information capacity or the maximum data rate that can be transmitted using any system. It can be expressed in this equation, or it can be expressed into b logarithm base 2 of 1 plus 10 raised to s over n in dB over 10. Substitute the values and we get 10 kilohertz times the logarithm base 2 of 1 plus 10 raised to 15 over 10, or we get 50,278.0767 BPS, or we can express in kbps as 50.2781 kbps. So this is the answer to this example. So the third example, what is the channel capacity for a signal power of 200 watts, noise power of 10 watts, and a bandwidth of 2 kilohertz of a digital system? So we have the given, the signal power, the noise power, and the bandwidth respectively. So we need to find the channel capacity, or better known as the information capacity. So we have this solution. We have this given formula, the Shannon's limit of information capacity formula. We substitute the values and we get 2 kilohertz times logarithm base 2 of 1 plus 200 watts over 10 watts, where we get 8,784.6348 BPS, or 8.7846 kbps. So this is the answer to this example. So for the first example, a system has a bandwidth of 4 kHz and a signal to noise ratio of 28 decibel at the input to the receiver. Calculate its information carrying capacity. So we have the given a signal to noise ratio, but in terms of decibel, which is 28 decibel, and a bandwidth of 4 kHz. So we have this solution where we substitute the values and we get 4 kHz times the logarithm base 2. This is the logarithm base 2 of 1 plus 10 raised to 28 decibel, or we get 252,527,829.378 BPS, or 2.5278 mega BPS. And the last example, it is at the input to the receiver of a standard telephone channel, the noise power of 50 microwatts and the signal power of 20 milliwatts. Calculate the Shannon limit for the capacity of the above channel under this condition. So we have the given signal power and noise power, and the given problem we have seen the bandwidth. However, we have given a clue that it is a standard telephone channel that had been used in this example. So we all know that the bandwidth for a standard telephone channel is 3 kHz. So we get the value of the bandwidth, and we substitute where we get 25,942.3753 BPS, or we can express in kbps as 25.9424 kbps. And that concludes my video presentation on Shannon limits on information capacity.